Okay, welcome everyone to today's lecture. So today we'll talk about group homomorphism. So a homomorphism of group means that a map between two groups with result features. So definition: like G and H being groups group homomorphism from G to H is a map from G to H such that it resembles binary. So the base K of FB equal to FA FB while A B belongs to G. Example: so the first example is a trivial one. Let G be a map A to the constant map G to G given everything to the neutral element of G is a group homomorphism called the trivial group homomorphism. G. Okay. Second example is that for any subgroup H of a group G, the inclusion map of H into G is a group homomorphism. This is also a trivial example. Okay. So in particular, the identity map, of G from G into G given by A goes to A is a group homomorphism. Okay. Now let us see some non-trivial example. Fix an integer m and consider the map phi m from z to z. You know that z, the set of all integers z, is a group with respect to addition of integers, right? So we define a map phi m given by sending any integer a to am. Okay, or am. So m times n is the addition of a with itself m times if m is positive, or if m is negative, then this is the meaning that addition of minus a with itself mod m time, and if m is 0, this is 0. Then im of a plus b equal to m times a plus b equal to ma plus mb equal to ia plus b, or a b and z. So phi m is a group homomorphism. The fourth example, the next example is that take r cross or r star is the set of a real number minus origin. Okay. So this is a group with respect to multiplication. Okay. Then consider a map a from r to r star given by sending x to e to the power x, exponential of x. Okay.
Now since f of xy equal to p to the power xy, so here r has the addition infinity to structure. So f of x plus y equal to e to the power x plus y is equal to e to the power x times e to the power y, because on r star we have a multiplication structure, so after this distribution, so we can write it as fx. So fx f y both are given to r star, right, and r star is in both cases to multiplication. So now that here this portion is product, and here the portion is addition. Right.
So this holds for all the x, y, and r. So f is a group homomorphism. Right. Next example is we consider the map from real line to the circle, and from r to s1. S1 is the unit circle, set of all complex numbers, complex numbers, so that mod z is equal to 1. Right. So this is a group with respect to multiplication. In fact, this is a circle also step. So here I can define a map given by t equals to e to the power 2 pi I t. Right. Note that e to the power 2 pi I t there is a non-zero complex number with modulus 1, so it's lies inside s1. So note that f of
s plus t equal to e to the power 2 pi I s plus t equal to e to the power 2 pi I s
times e to the power 2 pi I t equal to fs times ft or st in r. So f is a group homomorphism. Next example we talk about is that take the map phi from the additive group of real numbers to SL2R. SL2AR is basically the set of all 2 by 2 matrices. A belongs to M2 by 2 matrices with real entries, such that determinant of A equal to 1. Okay. So So this is a group with respect to matrix multiplication. Define a map phi by sending real number A to the matrix 1 0 A 1. Okay, so note that is this matrix has 0 and 1, so it is inside S into R. Now note that this is a group homomorphism because phi of A plus B equal to 1 A plus B 0 1, right? And note that this is nothing but the product 1 A 0 1 times 1 B 0 1, right? Because if you do the perform the multiplication you get 1,
and
and
this
this
entry
entry
is
is
basically
basically
b
B
plus
plus A,
a
and
and
so
so
on
on
and
and
so
so
on.
on.
So
So
this
this
is
is
equal
equal
to
to
phi
phi
A
a
phi
phi
B
b
for
for
all
all
A
a
B
b
in
in
R.
R.
So this
So
is
this
a
is a
group
group
homomorphism.
homomorphism.
Next
Next
example
example
is
is
you take the map, fix an integer and get the equal to 2, and consider the map psi from Z to ZL. ZL is the set of all converse classes of integer modulo n. So we send any element A to the class of A modulo n, converse class of A modulo n. So clearly this is a group homomorphism because psi of A plus B is equal to class of A plus B modulo n is same as class of A mod n plus class of B mod n. So this is equal to psi of A plus psi of B on A B in Z. So this is also a group homomorphism, right? Next example is a little more interesting. So we fix a prime number P and consider the map F from ZP to ZP. ZP is the converse classes of integers modulo P. So this is a group, right, with respect to addition. We are define a map F from Z to ZP given by sending a class of A integer A modulo P to A to the power P.
right.
So
So
this
this
is
is
equal
equal
to
to also
now note that this is also a group homomorphism because f of class of A plus class of P equal to f of class of A plus B equal to f of is equal to A plus B to the power P is equal to basically sum of P choose I A to the power P minus I times B to the power I equal to 0 to P, the binomial theorem, right? As the only non-zero terms in this expression after going modulo P that's left out is basically A to the power P plus B to the power P. Right. So this is nothing but f of A plus f of Q. Right. So this is also group homomorphism. This map is actually this map given by sending an integer class of integer to its speed power. This is called a Frobenius map. This is a group homomorphism. Okay. Next we take the map. From GLN R to R star, the determinant map, sending a matrix A to determinant of A. Note that this is a group homomorphism because f of AB equal to determinant of AB, and the basic property of determinant says that this is equal to determinant net times net B for all AB belongs to Cn and R. This is equal to Fn. Right. So this is also a group homomorphism. Next example is you take a map, you take fix type of G and an element A belongs to G, define a map FF from G to G given by conjugation by A, sending B to AB A inverse. Note that this is a group homomorphism because simply f of fa of BC equal to A BC A inverse is equal to AB A inverse times AC A inverse is equal to FAB FAC or BC in G. So there is also a group homomorphism. This is called a conjugation map. Okay. So this map is called conjugation by A. Okay. Okay, so we have seen 10 examples of group homomorphism. Okay. Exercise. For each integer and greater than equal to 1, let J and be the set upon integers K in Z, so that all is equal to K and Z is equal to N. So this is basically the set containing elements 1, 2, up to N. Okay. Now for H, sigma belongs to Sn. Sn is the foundation group of N symbols. Consider the map. Sigma tilde from Jn plus 1 to Jn plus 1 defined by sending, defined by sigma tilde of K. K is equal to sigma K if K belongs to Jn, and if it is just n plus K equal to n plus 1, we fix it if K equal to n plus 1. Okay, so clearly since sigma is bijective map, so is also bijective. It's clear. So the sigma tilde is a foundation. So sigma tilde is Sn plus 1. Okay, so now this gives an injective map. This gives a map. This defines a map set from Sn to Sn plus 1 given by sending sigma to this sigma as we have defined above. So verify that f is injective homomorphism. Using this injective group homomorphism, you can identify Sn as a subgroup of Sn plus 1 using f. We can give Sn as a subgroup Sn plus 1. Yeah. So the next we consider the point to fix an integer and get an equal to 2 and consider the map signature map from Sn to so given by sending any computation sigma to its signature, we will define to be 1 sigma is minus 1 if or 1. So now since sigma can any either even permutation or product of odd number permutation, it's actually utilitarian. Means can never write as permutation as well as product of odd number. So therefore because of this permutation is either even or odd. So the signature becomes a group of. So if sigma then sigma composed then sigma composed term is again number transfer. So total is this is just this is at least one of them is odd. Now to prove this, sigma 1 component